4 light-years from the ground beneath your feet. A relentless storm of extreme ultraviolet radiation lashes against a barren expanse of silicate rock. The star responsible for this bombardment is a red dwarf, small, volatile, and highly magnetic. It violently erupts on a regular basis, hurling plumes of high-energy plasma outward, effectively stripping away any delicate gases that might attempt to cling to the rocky mass orbiting intimately close to its fire. The surface of this neighboring world is a sterile, irradiated wasteland, permanently tidally locked by gravity. One hemisphere bakes in a perpetual, red-tinted twilight, while the other is plunged into eternal, frozen darkness. This is the physical reality of Proxima Centauri b, our closest planetary neighbor. We have spent decades mapping the faint, rhythmic dips in starlight as distant spheres pass across the faces of their host suns. Observatories floating in the vacuum of our own orbit have gathered enough precise photometric data to formulate an absolute statistical certainty. The math is undeniable. There are more planets in the Milky Way galaxy than there are stars. Hundreds of billions of rocky bodies suspended in the dark. The raw numbers dictate a crowded galaxy. The early statistical models promised an endless catalog of oceans, thick atmospheres, and stable climates. But as we pivot our most advanced instruments from merely counting these worlds to actually taking their temperature, measuring their thermal emissions, and dissecting the faint light reflecting off their crusts, a cold and heavy silence begins to settle over the data. We peer into the atmospheres of planets roughly the size of our own, hoping to detect the chemical signatures of equilibrium. Instead, we find worlds locked in a perpetual state of geological agony. We find planets choked by global oceans of molten lava, where the atmospheric pressure is so immense that rain falls as droplets of liquid iron. We find massive gas giants orbiting so close to their parent stars that their atmospheres are literally boiling off into the void, leaving long comet-like tails of escaping heavy metals. We find rogue planets, violently ejected from their home systems, drifting blindly through the interstellar medium at temperatures hovering just above absolute zero. Every time we upgrade our observational hardware, parsing the infrared spectrum with finer precision, the universe hands us a brutal reality check. The habitable zone, that delicate orbital band where liquid water can theoretically exist, is turning out to be an active battlefield. Unrelenting stellar winds, severe coronal mass ejections, and orbital chaos dominate the very spaces we once hypothesized might be quiet cradles of complex chemistry. The overwhelming majority of the cosmos is not merely indifferent to stability, it is actively hostile to it. We are forced to confront a growing, uncomfortable anomaly in our astronomical models. The galaxy is overflowing with planets, yet the physical mechanisms of planetary death drastically outnumber the mechanisms of survival. The universe appears to be operating under a set of physical laws that heavily favors rapid sterilization, leaving us staring at a vast, silent graveyard of shattered cores and suffocated atmospheres, searching the telemetry for the unseen variable that is systematically wiping the slate clean. The illusion of abundance is the first barrier we must dismantle. In the earliest days of exoplanetary science, our discoveries were framed with a sense of triumphant inevitability. Whenever a new planet was detected within the theoretical boundary of a star's habitable zone, the immediate assumption was that we were looking at another Earth, a blue and green marble waiting to be cataloged. We looked at the sheer volume of stars in our galaxy, ran the elementary calculations, and assumed that a high count of planets naturally translated into a high count of living worlds. But this early optimism was a product of our own geographical bias, a flaw in our collective intuition, born from growing up in an extraordinarily sheltered pocket of the cosmos. We treated our solar system as the default template for the universe, rather than what it truly is, a bizarre, highly anomalous sanctuary of stability. To understand why our intuition has failed so completely, we have to look closely at the historical shift in how we observe the dark. In the late 20th century, the detection of a single planet around another sun was a monumental, painstaking achievement. Early pioneers relied heavily on the radial velocity method, measuring the subtle, microscopic wobble of a star caused by the gravitational tug of an orbiting body. Because this technique inherently favors massive objects orbiting incredibly close to their parent stars, the first worlds we discovered were monsters. We found hot Jupiters, gas giants with scorching atmospheric temperatures that completed a full orbit in a matter of Earth days, defying every planetary formation model we had written down. Then came the Kepler Space Telescope, which revolutionized our understanding by monitoring over 150,000 stars simultaneously, watching for the transit method, the incredibly faint drop in light that occurs when a planet crosses directly between the star's disk and our point of view. Kepler taught us that small rocky planets are everywhere. The math shifted dramatically. Astronomers began calculating the occurrence rate of Earth-sized planets around sun-like stars, arriving at numbers that suggested billions of potential habitats in the Milky Way alone. However, the raw dimensions of a planet do not dictate its physical reality. The transit method tells us how wide a planet is. The radial velocity method tells us how heavy it is. Together, they give us bulk density, allowing us to separate the rocky spheres from the gas giants. But density is a silent metric. It tells us that a world is made of rock, but it remains entirely blind to whether that rock is a cradle or a furnace. Our current generation of instruments, spearheaded by the deep space infrared capabilities of the James Webb Space Telescope, has begun to strip away the assumptions. By analyzing transmission spectroscopy, capturing the starlight that filters through the thin outer rim of a planet's atmosphere during a transit, we can read the chemical fingerprints of these distant worlds. When a planet passes in front of its star, the gases in its atmosphere absorb specific wavelengths of light. By breaking that light down into a spectrum, we can see exactly what the atmosphere is made of, or if it even exists at all. What Webb is revealing is a profound, systemic devastation. The fundamental error in our initial intuition lies in how we defined the habitable zone. In classic textbooks, it is a simple mathematical equation based entirely on distance and stellar luminosity, a Goldilocks band where the temperature is just right for liquid water. But this formula treats stars as stable, static light bulbs. It completely ignores the brutal, dynamic physics of stellar evolution and space weather. Consider the most common stars in the universe, M dwarfs or red dwarfs. They make up roughly 75% of the entire stellar population of the Milky Way. If you are looking for a rocky planet in our galaxy, you are almost statistically guaranteed to find it orbiting a red dwarf. Because these stars are significantly smaller and cooler than our Sun, their habitable zones are compressed incredibly tight to the stellar surface. A planet in this zone must orbit so close that its year is measured in hours or days, not months. This extreme proximity introduces a catastrophic physical consequence known as gravitational tidal locking. The gravitational pull of the star acts as a relentless brake on the planet's rotation, eventually forcing it to sink completely with its orbital period. The planet is frozen in place. One side is condemned to an unending day of direct, unyielding stellar radiation, while the night side enters a permanent freeze, completely shielded from any warmth. In a traditional classroom model, you might hypothesize that an atmosphere could redistribute this heat, creating a temperate twilight zone along the border between day and night. But the physics of a red dwarf do not allow for such balance. During their youth, a period that can last for 1 billion years, red dwarfs are notoriously unstable. They undergo prolonged phases of hyperactivity, emitting frequent, massive superflares that are orders of magnitude more powerful than anything our Sun has produced in recorded history. Without a colossal, highly resilient magnetic shield, a planet locked in this close cosmic embrace faces complete atmospheric erosion. The high-energy X-ray and ultraviolet photons slam into the upper atmosphere, breaking apart water molecules into hydrogen and oxygen. The lighter hydrogen escapes into the vacuum of space almost instantly, while the remaining oxygen reacts with the surface rocks, leaving behind a rusted, dehydrated, and utterly suffocated world. The starlight we thought would give life instead acts as a slow, cosmic sandblaster, stripping the planet down to its naked, sterile crust. We are forced to realize that the existence of a rocky surface is not a guarantee of a future. It is simply the raw material that the universe uses to build its ruins. The vast majority of planets we have cataloged are not waiting for life. They have already survived their most violent eras and emerged completely spent, hollowed out by the very stars that brought them into existence. This is the true nature of the cosmos we are exploring. It is an intricate machinery designed for attrition, where the margins for survival are so razor thin that our own existence begins to look less like a natural consequence of physics and more like a bizarre, temporary structural leak in a hostile system. If you seek to understand the truth of what lies in the deep dark, to look past the comforting myths of an endless cosmic paradise and confront the universe exactly as the data reveals it, then join us. This exploration requires a mind willing to look into the cold facts without flinching. Subscribe to this channel and ensure you are present for the chapters yet to be uncovered as we continue to map the silent architecture of the void. To fully grasp the magnitude of this cosmic graveyard, we must abandon our terrestrial perspective and confront the sheer, staggering scale of the architecture involved. We are not looking at a localized phenomenon. We are looking at a fundamental feature of reality. The Milky Way galaxy alone is a sprawling, rotating disk of stellar material spanning over 100,000 light-years across. Within this immense structure, gravity has ignited somewhere between 100 billion and 400 billion stars. For generations, that number was treated as the ultimate upper limit of cosmic real estate. But the data retrieved from orbital observatories over the last 2 decades has forced us to multiply that unimaginable figure. Stars, as it turns out, do not form in isolation. They condense from vast molecular clouds of gas and dust, and the leftover debris from that violent ignition does not simply blow away. It coalesces, it flattens into a protoplanetary disk, a swirling, chaotic ring of raw material that begins to clump together through static electricity and eventually through the brute force of gravity. The math of planetary formation suggests that almost every single star in the night sky hosts at least one planet, and in most cases, an entire system of them. We are talking about trillions of individual, fully formed worlds within our galaxy alone, trillions of distinct geographical surfaces, trillions of atmospheres, trillions of chemical experiments playing out in the dark. Yet, as we peer closer at these individual experiments, the narrative of abundance collapses into a horror of extreme physics. The instruments we use to investigate these worlds do not take photographs. A planet is simply too small, and its host star is too blindingly bright to be captured by a traditional camera. Instead, we have to read the shadows. We capture the infrared light of the star and look for the microscopic, rhythmic dips in brightness that occur when a planet orbits its sun. But the true genius of modern astrophysics lies in what happens when the planet orbits behind the star and then emerges on the other side. This technique is known as a phase curve observation, and it has allowed us to map the temperature distribution of worlds we cannot even directly see. By continuously monitoring the infrared glow of the entire star system as a planet completes its orbit, we can separate the heat of the star from the heat of the planet. We can measure the thermal emission of the planet's day side, and then, as it rotates its night side toward us, we measure the drop in temperature. When we point our infrared sensors at a world designated as 55 Cancri E, an exoplanet roughly twice the diameter of Earth, the telemetry reveals a landscape that defies human comprehension. This planet sits so deep within the gravitational well of its host star that its year lasts less than 18 hours. The phase curve data tells us that the side of the planet facing the star is baking at a temperature exceeding 2,400 degrees Celsius. At this extreme thermal threshold, the very concept of a solid surface ceases to exist. The silicates that make up the planet's crust are not merely molten, they are boiling. The rock vaporizes, rising into the vacuum to form a thick, suffocating atmosphere composed entirely of gaseous minerals. But the phase curves also show us the dark side of this tidally locked world. And this is where the physics become truly merciless. The night side is cooler, but only by a margin. Because the planet is wrapped in a thick atmosphere of vaporized rock, supersonic winds, driven by the extreme temperature differential, carry the gaseous silicates from the day side into the freezing darkness of the night side. As the vapor crosses the terminator line into the shadows, the sudden drop in temperature forces the gas to condense back into a liquid state. The atmosphere literally precipitates magma on the dark side of 55 Cancri. It rains droplets of liquid stone, falling continuously into a global ocean of churning lava. There is no solid ground here. There is no water. There is only a relentless, deafening cycle of vaporization and condensation. And this is not an anomaly. It is simply one of the many categories of devastation we have cataloged. We call them lava worlds, and they are common. But the absence of water is not the only mechanism of planetary death. In fact, an overabundance of water presents its own unique brand of hostility. When we calculate the density of certain exoplanets, we find worlds that are significantly lighter than rock, but much heavier than gas. The only substance in the universe that fits this mathematical profile in such large quantities is water. We call them ocean worlds. To the human mind, the idea of an endless ocean sounds like a sanctuary, a global canvas for complex biology. But physics scales ruthlessly. An Earth-like planet is mostly rock, with a microscopic, fragile film of water resting on its surface. The oceans we know are mere puddles. The ocean worlds we are discovering consist of up to 50% water by mass. These oceans are not measured in kilometers. They are measured in thousands of kilometers of depth. As you descend into an ocean of that magnitude, the weight of the water above you compounds exponentially. At the bottom of these alien oceans, the pressure reaches levels that completely break the molecular rules we are familiar with on Earth. The water does not simply remain a liquid. The crushing arithmetic of gravity forces the water molecules to pack together into a highly dense, solid crystal matrix. It becomes an exotic form of matter known to physicists as Ice 7. This ice is not cold. It is scalding hot, compressed into a solid state purely by the tyrannical pressure of the deep. It forms an impenetrable mantle that completely seals off the liquid ocean above from the rocky core below. On Earth, the interaction between the rocky seafloor and the ocean water is the fundamental engine of the global thermostat. Hydrothermal vents spew minerals from the planet's interior into the water, driving a complex carbon silicate cycle that regulates the atmosphere and prevents the planet from turning into a frozen wasteland or a runaway greenhouse. It is the friction of geology that allows chemistry to evolve. But on a true ocean world, that cycle is severed. The rocky core is permanently entombed beneath thousands of kilometers of hot, solid ice. The ocean above is a sterile, stagnant abyss, cut off from any chemical nourishment. It is a world drowning in its own abundance, a global tomb of water where the basic mechanisms required to sustain equilibrium simply cannot function. These are the planets that remained bound to their stars. But what about the ones that did not? To truly comprehend the scale of the mystery, we must look into the darkest, coldest pockets of the interstellar medium. The formation of a planetary system is not an orderly, peaceful accretion of matter. It is a chaotic, violently unstable game of orbital billiards. As massive gas giants form in the outer reaches of a young star system, they begin to migrate inward, their immense gravitational fields pulling and pushing smaller, rocky worlds out of their orbits. The mathematical models of early system formation, n-body dynamic simulations, show us that for every planetary system that eventually stabilizes, multiple worlds are entirely ejected from the host system. They are violently slingshotted out of the gravitational grip of their suns and cast into the freezing void of deep space. We call them rogue planets, free-floating worlds, orphans. Because they emit no light and orbit no star, they are practically invisible to traditional telescopes. They are the ultimate dark matter of exoplanetary science. But gravity always leaves a footprint. We find them using a phenomenon predicted by Einstein's theory of general relativity, gravitational microlensing. When an object of sufficient mass drifts directly between our telescopes and a distant background star, the gravity of the drifting object bends the very fabric of space-time around it. It acts as a transient, ghostly magnifying glass. The light from the background star doesn't travel in a straight line. It curves around the invisible planet, causing the star to briefly spike in brightness before fading back to normal. By carefully analyzing the duration and intensity of that flash, we can calculate the mass of the invisible ghost that passed in the dark. The surveys dedicated to scanning the galactic core for these microlensing events have returned a chilling verdict. For every star that burns in the Milky Way galaxy, there are likely multiple rogue planets drifting in the absolute darkness between them. The math points to an unimaginable reality. There could be trillions of rogue planets wandering blindly through our galaxy alone. The majority of terrestrial worlds in the cosmos may not be orbiting suns at all. They are frozen solid, plunged into an eternal night, just a few degrees above absolute zero, drifting through the interstellar dust without a dawn, without a season, and without a future. Our sun is merely a campfire in a dark forest, and the woods are filled with the frozen corpses of worlds that were cast out into the cold billions of years ago. The scale of this attrition demands a reevaluation of our place in the cosmic order. The universe is not a machine designed to create habitable environments. It is a machine that creates temporary structures, grinds them against the abrasive forces of stellar radiation, orbital chaos, and gravitational decay, and eventually recycles them into dust. We see the end stage of this recycling process when we observe the oldest, most exhausted objects in the galaxy, white dwarfs. When a star like our sun exhausts its nuclear fuel, it violently expands into a red giant, incinerating its inner planets, before shedding its outer layers and collapsing into a white dwarf. A white dwarf is a dead stellar core, incredibly dense, roughly the size of the Earth, but containing half the mass of a sun. Its gravity is so intense that any heavy elements present on its surface should be instantly dragged down into the core, disappearing from view. A pure white dwarf should only show the spectral signatures of hydrogen or helium. Yet, when we point our spectrographs at these dead stars, we frequently find something deeply unsettling. We see the heavy, unmistakable spectral lines of calcium, iron, magnesium, and silicon in their outer atmospheres. We are literally watching the metallic rain of pulverized planets. The chaotic gravitational shifts that occur during a star's death spiral often send the remaining, surviving planets crashing inward. The sheer tidal forces of the white dwarf rip these worlds apart long before they impact, shredding them into vast disks of planetary debris. That debris then spirals down onto the surface of the dead star. What we are reading in those spectral lines is the literal autopsy of a shattered solar system. We are measuring the chemical composition of alien continents, alien mountain ranges, and alien mantles, all reduced to a toxic vapor burning in the atmosphere of a stellar corpse. Everywhere we look, across every wavelength of light, the evidence points in a single, unwavering direction. The cosmos is a highly efficient engine of destruction. We are standing on an incredibly rare, temporal anomaly, a world that has somehow dodged the hyper-violent flares of its youth, maintained a delicate orbital balance, and retained a thin, fragile layer of gas against the relentless vacuum of space. The silence of the universe is not the silence of an empty room. It is the silence of a battlefield long after the war has ended. The worlds are out there. The raw materials are abundant, but the mechanics of the void ensure that the vast, overwhelming majority of them are dead on arrival. We seek comfort in the rhythmic predictability of our own world. We watch the sun rise and set. We track the predictable arc of the moon, and we assume that the mechanics governing our local environment are a permanent fixture of reality. We have been lulled into a false sense of security by the incredibly short lifespan of human observation. From our deeply limited perspective, the architecture of the solar system appears as an immaculate clockwork mechanism, bound by the rigid, unchanging laws of Newtonian gravity. But the mathematics of orbital dynamics hold a dark and deeply unsettling secret. A structural flaw built into the very foundation of physics that guarantees this stability is nothing more than a temporary, localized illusion. When we calculate the gravitational interaction between two isolated objects, a solitary planet orbiting a single, quiet star, the equations are elegant, perfectly solvable, and eternally predictable. You can plot their coordinates infinitely into the future or mathematically trace them back into the deep past with absolute precision. But the moment you introduce a third gravitational body into that system, the mathematics entirely shatter. This is known in astrophysics as the n-body problem. The equations instantly become nonlinear and chaotic. The gravitational tug of every planet pulling on every other planet creates an infinitely complex feedback loop that simply cannot be resolved with an exact mathematical solution. More than a century ago, mathematicians mapping the geometry of space realized that our solar system is not a stable configuration. It is a dynamically chaotic system operating on a delayed, invisible fuse. Today, we use immense supercomputers to run numerical integrations, painstakingly simulating the orbital paths of our neighboring planets millions of years into the future. What these high-fidelity models reveal is a mathematical boundary known as the Lyapunov time. This is the precise chronological horizon beyond which predictive physics utterly breaks down. Because the system is governed by chaos, an infinitesimally small error in our current measurements, a difference of a few millimeters in the position of Jupiter, or the microscopic gravitational influence of a passing comet, multiplies exponentially over time. Fast forward the simulation far enough, and the predicted orbits begin to warp, destabilize, and violently intersect. The mathematics dictate that over a long enough timescale, planetary ejection is not an anomaly or a freak accident. It is the default, inevitable resolution of gravitational chaos We cannot mathematically prove that the Earth will safely remain in its orbit. The equations allow for a perfectly valid future where the delicate orbital resonance of the inner planets finally destabilizes, sending our world careening directly into the sun or violently ejecting it outward into the interstellar freeze. We are not riding on a track. We are balancing on the edge of a gravitational blade, and the math guarantees that eventually the system will slip. This limitation in our predictive math is only the first barrier. When we turn our gaze outward, attempting to map the graveyard of the galaxy and understand the sheer scale of the dead worlds surrounding us, we slam into a far more absolute physical wall. The finite speed of light. The equations of electromagnetism dictate a strict, unbreakable speed limit for the transmission of information across the void. Because distances in the cosmos are so incomprehensibly vast, the telescopes we build are not observing the universe as it currently exists. They are observing a localized historical illusion. We are permanently trapped in a chronological delay, forced to study the universe through the lens of a deep, inescapable lag. When we analyze the atmospheric composition of a rocky exoplanet 50 light-years away, we are looking at the photons that left that world 5 decades ago. If that planet was completely sterilized by a hyperviolent stellar flare yesterday, peeling its atmosphere into the void and scorching its crust to glass, the physical evidence of its destruction will not reach our instruments for another half-century. We are perpetually mapping a ghost town, cataloging worlds that may have already been incinerated, shattered, or frozen solid long before our advanced instruments even detected their faint silhouettes. The deeper we peer into the cosmos, the more severe this delay becomes, meaning our map of the universe is largely a map of things that are no longer there. But the true horror of this observational barrier is not merely the delay. It is the terrifying reality that the universe is actively, physically severing our connection to the rest of the cosmos. The fabric of space-time itself is not a static stage where the events of the universe play out. It is a dynamic, stretching entity. When we analyze the light arriving from the most distant galaxies, we find that the light waves have been physically stretched as they travel through expanding space, shifting their colors toward the red end of the spectrum. For decades, the assumption was that the gravitational pull of all the matter in the universe would eventually act as a cosmic brake, slowing this expansion down. But the observational data delivered a shock that fundamentally shattered our cosmological models. The expansion is not slowing. It is actively accelerating, driven apart by a relentless, unseen repelling force that we simply call dark energy. The mathematics of dark energy reveal a chilling, inescapable future trajectory. As space expands faster and faster, it carries distant galaxies away from us at velocities that eventually exceed the speed of light. This is not a violation of relativity, because the galaxies themselves are not moving through space faster than light. The space between us is simply swelling at an uncontrollable, exponential rate. This stretching of reality creates a cosmological event horizon. It is a hard, absolute mathematical boundary beyond which the light from distant stars will never be able to reach us. The photons they emit are fighting against a current of expanding space that is simply moving too fast. Like a swimmer trying to progress up a violently accelerating waterfall. Every single day, entire galaxies slip quietly over this horizon, passing the mathematical threshold where their light is permanently cut off from our view. They vanish out of our observable universe forever, never to be seen or interacted with again by any future generation, no matter how advanced our technology becomes. We are stranded on a cosmic island, and the ocean is stretching so rapidly that soon the night sky will be scrubbed completely clean of distant light. The math dictates a future where the universe appears utterly empty, isolating whatever survives in absolute darkness. This inexorable isolation forces us to confront the statistical paradox of our own existence, often framed as the Great Filter. In popular culture, this concept is usually reduced to a philosophical musing about alien civilizations hiding in the dark or annihilating themselves with technology. But to the astrophysicist, the Great Filter is not a science fiction concept. It is a strict, undeniable problem of thermodynamics. The second law of thermodynamics is arguably the most unyielding, merciless law in all of physics. The total entropy or disorder of an isolated system can never decrease over time. The physical universe has a fundamental mathematical preference for chaos, radiation, and atomic dispersal. Any complex structure, whether it is the delicate orbital resonance of a planetary system, the chemical equilibrium of a breathable atmosphere, or the incredibly intricate biological machinery of a living cell, is a temporary, localized rebellion against this universal law. Maintaining physical order against the crushing weight of entropy requires a continuous, massive expenditure of energy and an incredibly delicate balance of variables. The statistical probability of a planet maintaining a highly ordered, stable environment against the relentless, chaotic radiation of its host star, the gravitational perturbations of its rogue neighbors, and the violent impacts of interstellar debris for billions of years is infinitesimally small. The math suggests that the Great Filter is not a single, catastrophic event waiting in our future, but rather the constant, grinding friction of the universe itself. The cosmos is a thermodynamic shredder. The sheer abundance of dead, irradiated, and frozen worlds we observe is simply the physical manifestation of entropy ruthlessly reasserting its dominance over matter. Biology and geological stability are mathematical anomalies, structural errors that the universe naturally corrects through extreme heat, extreme cold, or absolute vacuum. Yet, even our understanding of entropy, matter, and gravity eventually hits a terrifying, insurmountable wall. We have built two towering mathematical frameworks to describe reality: general relativity, which brilliantly governs the macroscopic universe of gravity, massive stars, and curving galaxies, and quantum mechanics, which flawlessly governs the microscopic, hyperactive realm of atoms, photons, and subatomic particles. In almost every corner of the observable universe, these two rulebooks operate independently, but there are places in the deep dark where the universe physically forces them to collide. And when they do, our mathematics entirely collapse. When a star significantly more massive than our own sun exhausts its nuclear fuel, the outward pressure of its fusion engine ceases. The core, no longer able to push back against the staggering, accumulated weight of its own outer layers collapses inward in a fraction of a second. If the remnant core is heavy enough, passing a strict mathematical threshold known as the Tolman-Oppenheimer-Volkoff limit, the gravitational force becomes absolute. It overcomes the strong nuclear force that keeps atoms intact, violently crushing electrons and protons together until they merge into a dense sphere of pure neutrons. But if the initial mass of the star is even greater, even the immense structural integrity of tightly packed neutrons shatters. Gravity turns into a tyrant that cannot be balanced by any known physical force. The mass collapses infinitely inward upon itself, ripping a hole in the fabric of reality. This is the birth of a black hole. The boundary surrounding it is the event horizon, a spherical point of no return where the escape velocity required to leave the gravitational well exceeds the absolute speed of light. Anything that crosses this threshold, planets, light, radiation, information, is dragged inward. But the true horror lies not at the edge, but at the absolute center. According to the equations of general relativity, all the mass of the collapsed star and any dead worlds it has swallowed is crushed into a point of zero volume and infinite density, a singularity. In the rigid language of theoretical physics, when your mathematics produce an infinity, it does not mean you have successfully discovered an infinite physical object. It means your theory has fundamentally broken. It means you have reached a place where the laws of nature, as we understand and measure them, no longer exist. At the singularity, the curvature of space-time becomes mathematically infinite. Time, as a measurable chronological progression, stops entirely. Space loses all meaning. Gravity becomes so intense that it generates a profound theoretical impasse known as the information paradox. Quantum mechanics strictly dictates that the fundamental information of the universe, the precise atomic arrangement of the matter that fell in, the history of the dead planets that were consumed, cannot be permanently destroyed. But general relativity dictates that inside a black hole, behind the inescapable veil of the event horizon, that information is utterly erased from reality. We are left staring into absolute, freezing darkness, armed with incredibly precise equations that violently contradict each other, trying to map a structure that actively deletes the physical laws we use to measure it. The deeper we peer into the architecture of the cosmos, desperately looking for the underlying foundation of reality, the more we find regions where reality itself refuses to operate, leaving us completely blind before the sheer crushing weight of a mystery that physically consumes the light required to solve it. This systemic deletion of physical law and historical record forces a profound shift in how we must view our own future. We look at the Earth, with its deep oceans, stable continents, and predictable seasons, and we instinctively treat it as a permanent monument. We map our future in centuries and millennia, assuming that the ground beneath our feet is a fixed stage upon which the human drama will play out indefinitely. But the brutal reality of astrophysics strips away this illusion of permanence. Planetary death is not merely a distant phenomenon occurring in the chaotic, violent corners of the galaxy. It is a scheduled, mathematically unavoidable event in our own local neighborhood. The engine that sustains our fragile ecosystem is a ticking clock, operating on a strictly limited supply of fuel. Our sun is currently in its main sequence, maintaining a delicate, beautiful stalemate known as hydrostatic equilibrium. At this very moment, the crushing, unfathomable weight of the sun's own gravity is pulling millions of tons of matter inward, trying to collapse the star. This collapse is only halted by the violent nuclear fusion occurring in the core, where hydrogen atoms are slammed together to create helium, releasing an outward pressure of radiation that exactly balances the inward pull of gravity. It is a brilliant, roaring mechanism, but the math of nuclear physics is absolute. The hydrogen will run out long before the sun enters its final, violent death throes. The architecture of our planetary system will fundamentally change. In approximately 1 billion years, the subtle mechanics of the sun's core will cause its luminosity to increase by roughly 10%. To a human lifespan, this shift is imperceptible. To a planetary climate, it is a death sentence. This slight increase in solar radiation will push the Earth completely out of the habitable zone. The global temperatures will rise just enough to trigger a runaway moist greenhouse effect. The oceans will begin to evaporate at a catastrophic rate, pushing immense volumes of water vapor high into the stratosphere. There, stripped of the protective magnetic shielding found closer to the surface, the raw ultraviolet radiation of the sun will effortlessly break the chemical bonds of the water molecules. The heavy oxygen atoms will fall back down to oxidize the surface crust, while the lighter hydrogen atoms will be swept away by the solar wind, escaping into the vacuum of space forever. Earth will not die in a sudden, cinematic explosion. It will be slowly, methodically dehydrated over millions of years. The carbon silicate cycle that regulates our atmosphere will shut down. Plant life, starved of carbon dioxide and water, will asphyxiate. The Earth will be reduced to a scorched, sterile rock, resembling the current state of Venus, trapped in a suffocating envelope of toxic heat. And the sun will not stop there. As the core runs entirely out of hydrogen, the hydrostatic equilibrium will fail. Gravity will finally win the first battle, crushing the core inward until the immense pressure and temperature ignite the helium ash left behind. This secondary ignition is violent, forcing the outer layers of the sun to swell to monstrous proportions. Our star will transform into a red giant. The searing plasma of the sun's outer atmosphere will expand outward, physically swallowing the orbits of Mercury and Venus, instantly vaporizing their rocky mantles into gas. As the sun's atmosphere approaches the orbit of the Earth, the mechanics of our destruction become grimly mechanical. Even if the expanding plasma does not directly engulf our planet, the intense friction of the Earth moving through the extreme outer edges of the sun's bloated atmosphere will act as an orbital brake. Our forward momentum will bleed away. The Earth will slowly, inevitably spiral inward, plunging into the deep, stellar atmosphere until tidal forces shatter the crust, and the remnants of our world are melted down into their base atomic components, absorbed completely into the star that created them. During this catastrophic expansion, the habitable zone of our solar system will be violently shoved outward into the freezing dark. For a brief, fleeting window in deep time, the ice moons of Jupiter and Saturn, Europa, Ganymede, Enceladus, and Titan will experience a sudden, radical spring. their global shells of rock-hard ice will melt, exposing vast, deep-water oceans to the light of the bloated red sun. Organic chemistry might briefly spark in these newly thawed abysses, but this era of outer system habitability is a cruel, temporary mirage. The red giant phase is unstable. The sun will eventually exhaust its helium, triggering a final series of massive thermal pulsations. The star will convulsively shed its outer layers, blowing them away into the interstellar medium, leaving behind nothing but the naked, glowing core. A white dwarf. The immense heat source will vanish. The sudden drop in temperature will plunge the entire solar system back into absolute darkness. The brief oceans of the outer moons will freeze solid once again, this time permanently, locking any newly formed chemistry in a tomb of ice just degrees above absolute zero. The remaining planets, orbiting a stellar corpse, will join the ranks of the dead worlds we now observe in the deep dark. Faced with this absolute local deadline, the instinct of a surviving civilization would be to migrate, to look up at the hundreds of billions of stars in the Milky Way, calculate the trajectories, and cross the interstellar void to find a new, young sun. But the overarching reality of the cosmos offers no true sanctuary, only a change of scenery in a fundamentally hostile environment. The most logical destination for long-term survival would be a red dwarf. Because they burn their fuel at a fraction of the rate of our sun, a typical red dwarf can live for trillions of years. They are the ultimate cosmic marathon runners. The universe is only about 13.8 billion years old. Not a single red dwarf in the entire history of the cosmos has died yet. They offer an almost unimaginable stretch of deep time. But as we have mapped out in the data, this longevity is a trap. To live around a red dwarf is to live in the crosshairs of a volatile, hypermagnetic weapon. The violent superflares and the lethal tidal locking create a paradox of survival. The only stars that offer enough time for the civilization to achieve true permanence are the exact stars whose physical mechanics are designed to violently strip planets down to their sterile bedrock. The universe provides the luxury of time only in environments that are fundamentally hostile to complexity. This leaves us navigating a reality where safe harbors are nothing more than temporary structural anomalies. But the consequences of the physics we have uncovered extend far beyond the death of our solar system or the lethal mechanics of neighboring stars. They dictate the ultimate, unavoidable fate of the universe itself. The cosmos is currently in what astrophysicists call the stelliferous era, the era of starlight. It is a period defined by the violent, energetic ignition of gas clouds, the birth of galaxies, and the warmth of fusion. But this era is mathematically finite. We are living in a brief, sparkling cosmic spring. The overwhelming majority of the universe's timeline is completely dark. As the billions of years stretch into trillions, the mechanics of star formation will grind to a halt. The vast, swirling clouds of interstellar hydrogen, the raw fuel required to forge new stars, will eventually be entirely consumed or dispersed by the violent deaths of the stars that came before them. The galaxies will run out of gas when the last massive blue stars go supernova and the last stable yellow suns expand and shed their envelopes. all that will be left are the red dwarfs. And eventually, trillions of years from now, even the longest living red dwarf will run out of fuel. It will not explode. It will simply fade, cooling down to become a black dwarf, a cold, dead sphere of highly compressed carbon drifting silently through an expanding void. When the final star extinguishes, the universe will enter the degenerate era. The night sky, if anyone were left to observe it, will be entirely black. The cosmos will be populated exclusively by the remnants of the violent past: black dwarfs, ultra-dense neutron stars, frozen rogue planets, and black holes. During this incomprehensibly long, dark winter, the universe will not be static. The subtle, relentless forces of gravity will continue to dismantle whatever structures remain as the dead stars and frozen planets orbit each other in the pitch black. Their movement will generate incredibly faint ripples in the fabric of space-time, known as gravitational waves. These waves carry energy away from the system. It is a slow, agonizing process of orbital decay over timescales that break the human capacity for measurement. Every surviving planet will lose its forward momentum, spiraling inexorably inward until it crashes into the dead star it orbits. Whole galaxies will collapse. The remaining stellar corpses will slowly fall into the supermassive black holes, lurking at the center of their respective galactic remnants. The architecture of reality will be reduced to isolated, supermassive black holes, separated by distances so vast that the accelerated expansion of the universe ensures they will never interact. Yet, even these ultimate engines of destruction are not immune to the fundamental laws of thermodynamics. In the absolute deepest stretches of time, countless trillions of years after the last star has died, the mathematics of quantum mechanics dictate that black holes themselves will begin to leak. Through an incredibly slow, complex interaction at the very edge of the event horizon, particles will escape the gravitational grip of the singularity. This phenomenon, known as Hawking radiation, means that black holes are actively, imperceptibly evaporating. The mathematics reveal a merciless truth. The smaller the black hole, the hotter it burns, accelerating its own evaporation into the void. It will take an unimaginable span of time, a number of years followed by nearly 100 zeros, for the supermassive black holes to fully evaporate. But the end is a mathematical certainty. As the final mass of the last black hole radiates away into the expanding void in a brief, blinding flash of high-energy gamma rays, the universe will achieve its ultimate, inescapable state: maximum entropy, the heat death of the universe. All matter, all energy, all the broken remnants of trillions of dead worlds will be perfectly, evenly distributed across an infinitely large, infinitely cold expanse of stretching space-time. There will be no stars, no planets, no atoms, no light. The temperature of the entire cosmos will drop to a fraction of a degree above absolute zero, uniform in every direction. In physics, time is not simply a ticking clock in the background. Time is measured by the progression of events, by the movement of energy from a state of order to a state of disorder. When maximum entropy is reached, there is no more energy left to move. There are no more events that can possibly occur in a universe where absolutely nothing happens, where the physical temperature is perfectly flat and nothing changes. The the very concept of time ceases to have any physical meaning. The universe will not just be empty, it will be timeless, a frozen, infinite stillness that lasts forever. Every planet we discover today, every scorched crust, every frozen ocean, and every atmosphere boiling away into the dark is simply a momentary stepping stone on the universe's long, irreversible march toward this absolute zero point. We are observing the symptoms of a thermodynamic decay so vast and so absolute that our own existence begins to feel less like a triumph of biology and more like a brief, localized rounding error in an equation that demands total silence. We are that localized error, a momentary spark in a vast mechanical architecture that is slowly, inevitably powering down. For centuries, we have looked up at the night sky and projected our own biological imperative onto the dark. We imagined a universe waiting to be colonized, an endless frontier of virgin worlds perfectly tailored to host human ambition. We assumed that consciousness was the ultimate goal of cosmic evolution, that the universe was somehow waking up through us, and that our presence here was a permanent, necessary feature of reality. But the telemetry does not support our arrogance. The data reflects a cosmos that is entirely indifferent to the concept of biology. Consciousness is not the pinnacle of universal design. It is a profound thermodynamic anomaly. It is an incredibly fragile, energy-intensive configuration of atoms that the universe tolerates only under the most exceptionally rare and temporary conditions. The physical mechanics of reality heavily favor the silent, the frozen, and the dead. The universe does not want to be observed. It simply wants to reach equilibrium. We are standing on a fragile ghost ship, sailing through an endless ocean of shattered worlds. Every time our space telescopes capture the microscopic shadow of an exoplanet, every time we map the phase curve of a molten crust or measure the heavy metallic rain of a collapsing atmosphere, we are looking at the true default state of existence. The lava worlds, the suffocated gas giants, and the frozen wanderers cast violently into the interstellar void are not the failures of the cosmos. They are the standard operating procedure. We are the fleeting exception, a statistical glitch, living on borrowed time, sustained by a dying star in a galaxy that is actively, continuously bleeding its energy into the expanding dark. There is a deeply unsettling clarity in this realization. It strips away the comforting illusions we have built to shield ourselves from the true scale of the void. When you strip away the science fiction, the philosophical safety nets, and the mythologies of a welcoming cosmos, you are left with the cold, raw mathematics of attrition. We are entirely alone, not because life is an unrepeatable miracle, but because the machinery of the universe is a flawless, highly efficient sterilizer. The margins for error are absolute zero. We build our massive radio dishes in the quietest deserts on Earth, pointing them at the galactic core, waiting for a signal, a whisper, or any faint confirmation that another intelligence has successfully navigated the cosmic gauntlet. We expect a crowded universe because we cannot fathom our own impermanence. But the silence we hear when we tune our instruments to the deep dark is not a technological barrier we have yet to cross. It is the sound of the thermodynamic shredder operating exactly as designed. It is the cold, lingering echo of billions of worlds that sparked, choked, and went dark long before the first primitive oceans formed on our own planet. The night sky is not a canvas for our future. It is a sprawling, meticulously catalogued graveyard. And as we continue to drift through the outskirts of the Milky Way, clinging tightly to a microscopic layer of gas on a cooling rock, all we can do is measure the ruins, calculate the exact rate of the decay, and listen to the absolute, unbroken silence of the dead worlds falling deeper and deeper into the dark.